Uh, Good evening to all the students. Welcome to extra week session for this electrical machines 2 course. So this is a 1 hour extra session we are going to take today. So in this session, we will most likely be discussing the overall summary of the topics we have discussed over the weeks, starting from the week one, how we have progressed, and mainly we will be looking at few key numericals that will be based on the core concepts of each week's concepts. So yeah, during that particular week we did have discussed these problems, but now it's like a revision of these numericals again, which will touch the concepts we have been discussing since week one. So in this 1 hour time, we will see how many, as much as problems we could cover. So yeah, let's proceed. So here, this is from the week one concepts of magnetic circuits and the transformer actions we have discussed. So we discussed like the dot convention, how the dot convention should be, and what are all the principles that a transformer would hold, the inductance calculations, inductance formulas, what are the relations between inductance, reluctance, flux, MMF, these kind of relations. They're very important and key. So if you have forgotten them, let's revise them in this week again. We'll just have a quick look at the key concepts that we have gone through in the week one of our discussion. So let's see this numerical quickly. Two coils of an ideal transformer were given. We can see those coils A, B, and CD. So these two coils have the turns ratio is also given. 300 turns in the coil 1 AB and 200 turns in the coil CD. Now the terminals of coil AB is marked with dot, right? So we can see a dot marked at the AB coil, and the self-inductance of the same coil is also given 3.6 Henry. Now we can see there is a series connection that is being labeled in the color green at the bottom. The two coils are connected in series as shown in the picture. Now assuming all the leakage fluxes are negligible. So assuming all the leakage fluxes are negligible, we need to find out what is the terminal of the coil CD. In which terminal of the coil CD should we mark the dot terminal. So yeah, who are just joined, I'm just telling them. So this week's is an extra session where we will be revising all the numericals which we have been discussing over the weeks. So every week we are being going through some concepts, core concepts. So I have picked such numericals we have discussed during that specific week, and we will be reiterating now to touch upon those concepts again, so that you won't be forgetting those topics, and you will it will help you to reiterate those concepts once again with me. So yeah, we were looking at this problem where we were given all the details about the transformer turns ratio and also the self-inductance. The question which was asked is which terminal of the coil CD should be marked with a dot. So do you remember anything you want to say from your side? Any idea? How should we proceed with this? How can we find the terminal in the CD which should be marked with a dot? Any idea? It has to do something with the right hand thumb rule. So you know if a current passes through a coil, you know how the flux would be, a right hand thumb rule. So in a series, you know how the current would flow, and based on the current entering and leaving, you can mark the dot. If that rang any bell, if that helps you to um, solve the question, maybe you can try now. Okay, let's see. So let's say if a current being passed through the coil AB here, here I'm passing the current. The current is passing in this way, and the current enters the A at the dot. So if the current is entering at the dot A, the dot in the CD coil should also enter at the terminal. See, Let's say if current is entering here. Now, in the CD, dot should be at such point, either D or C, where the current also enters. Understood? That's the dot. The dot polarity says that the dot should be placed in such a way where the current is entering or leaving with respect to the first dot. In the coil AB, we see that the current is entering the dot A. So in the coil CD, the dot should be placed in that terminal where the current enters. So before placing the dot in the CD, let's see how the current enters or leaves in the terminal CD, right? So first analyze the current direction in the coil A, B, and CD, and wherever the current enters in CD, we will just right away put the dot. I'm just erasing the dots again. So that first we will analyze the circuit wherever the current is flowing, and then we will just place the dot right away. Okay, I have make the current pass through the A terminal here. So the flux in the AB coil would be clockwise or anti-clockwise. Okay, those who have joined now, I'm just giving a brief introduction of what we are doing today. This is an extra session, a 1 hour extra session we are having. Just look back at all the key numericals and concepts we have been discussing over the weeks, starting from week one. I want to touch those numericals which you have seen in the week specifically, so that we can reiterate the concepts again and help you get back those discussions again in mind. So yeah, so I have flown the current in the coil A. What would be the direction of flux in the coil AB? Is it clockwise or anti-clockwise? Uh, Using the right hand thumb rule, you can type it in the chat box, clockwise or anti-clockwise. So current flows like this, right? Current is flowing like this, right hand thumb rule. It would be anti-clockwise. So in this way. Now the flux in CD is also anti-clockwise because they both are connected in series, right? So since the both coils are connected in series, the flux through the coil CD will also be in the anti-clockwise direction. So if there is no series connection present, we know due to the transformer action there will be a cause and effect kind of flux, that the main flux and the induced flux would oppose each other. But since it is series connected coils, both the flux should aid and both should be anti-clockwise. So in order to be flux should be anti-clockwise in CD, what should be the current direction in this? So anti-clockwise means right here, in this fashion it should be, right? So it should be like this, and this one it should be like this. So this is how the current direction should be. Now it's simple. You just have to look at the terminal C and D. Wherever the current is entering, that should be the dot. Because in the coil AB side, the current is entering at the terminal A. Now see at the CD, wherever the current is entering, if the C it is entering and D it is leaving. So immediately you can mark the answer as terminal C. So this is the important dot concepts. If there is no series connection, the flux directions would be different. We can't comment on this flux direction as a series and AD. So it's just the series connection makes us to know the flux direction in the coil CD anti-clockwise. So now suppose the 150 volts RMS AC source I am connecting between A and B. The coil CD is left open. The two coils are connected in series as always. Now then calculate the RMS value in volts between the terminals A and C. I hope you guys remember how we have solved this problem. It's a very simple problem. So input we know the voltage, and output we know VCD, that also is open circuited. There is some voltage there, and we are asked the voltage of between potential difference between A and C, VAC. So how can we calculate it? So for that, let's calculate the voltage at the CD first. So then we will see how we can calculate. Okay, the idea is voltage here is given, that is 150 volts, that is V1, and we don't know what is V2, and we were asked the potential difference between these two. Okay, VAC. If you look like this, it will be a very simple problem now. It's like a circuit with three voltage sources in series. Now, you do the KVL and let me know the answer, because V1 we know 150, but what about V2? How can we get the V2? You know the voltage and turns ratio, right, for a transformer? V1 by V2 is equals to N1 by N2. So using this, quickly tell me what V2 value is.
100, sir.
Yes, 100. So N2 is 200, N1 is 300 into multiplied by 150. So 2 by 3, 1.5, 1.5 and 150 it will give you 100 volts. So since V2 is 100 and V1 is 150, it's a simple KVL now, right? Minus 150 plus VAC plus 100 is equals to 0. Now it will give you VAC is equals to 50 volts. Okay, you don't have to worry how can we calculate the potential difference between terminals A and C. It's just the series connection makes it a closed circuit. So with that you can directly calculate the voltage across the VAC if you know the voltage V1 and V2, right? Okay, now self-inductance. So these are some important formulas now we are going to discuss today. Um, Inductance formula we have discussed in the first week. So anyone remember the inductance formula? In the question, we were given the inductance of the coil AB, that is 3.6 Henry.
Sir, can you ask regarding the date?
I can't hear you, Desh. Can you be a bit more clear?
Date.
I'm saying something and I don't.
Hello?
Yeah, please say. I'm saying something.
Hello?
Yes, Dinesh, you can go on. Okay, fine. You can mute yourself. I can't hear you. Hopefully, I'm not disturbing anything. So, the self-inductance of coil 1 is given is 3.6 Henry, and L2 is being asked by us. So, if you remember, the formula for inductance N5, that is flux linkage to the current flowing through the coil. That's what we discussed, right? So L would be N5 divided by I. Now for the coil L1, N1 Phi1 divided by I1. But in the circuit we only know N. We don't know all these two terms. And you know the current flowing through I1 and Phi1 would be different from current flowing through the N2. So we can't um, use these two unknown terms which will be varying with respect to the coil. So we need to get this relation into a term which is common to the core. So let's interchange this N5 by I into something that is only dependent on constant term. That is terms we know, and maybe some other term which will be common for both the coils L1 and L2. So I'm changing this N1 N1 I know, I'm making it as it is. Now we know flux is equals to MMF by reluctance. Now reluctance of the core is same for both the coils L1 and L2. So I'm writing it flux, MMF is Ni, right? N1 I1 divided by I1 into reluctance R. Now I1 would get cancelled. L1 is equals to N1 square by R. So this is that kind of relation which can also make it relatable for the second coil. So L2 is nothing but N2 square by R. So now I know L1 and L2 relation where I also know the L1 value. So L1 is equals to N1 square by R. L2 is equals to N2 square by R. Now take the fraction of both L1 by L2. We need L2 ultimately. So N1 square divided by N2 square, the R and R gets cancelled. So you know all the terms except for the L2. A simple calculation. I hope you will calculate this. L2 is equals to N2 by N1 whole square multiplied by L1. So L1 is already given 3.6. So you should get a value of 1.6 Henry. So the important concept here is we need to get the terms into that parameters which are constant for the both coils L1 and L2. So yeah, so estimate the mutual inductance between the two coils A, B, and C, D. So mutual inductance is denoted by the alphabet M, right? M, A, B, C, D is asked. So any idea how can we get the M?
The N1 and 2 by reluctance, right?
Right, exactly. That's good. So L1 we already know N1 square by R, but when we derive the expression for mutual, it depends on not just its own turns, but the turns of the both the coils. So formula for mutual would be N1 N2 by reluctance. Now M is the one we need to calculate, and N1 N2 we know, but again reluctance we don't know. So simple, take the ratio of it again. L1 by M is equals to N1 square by N1 N2. From this relation, you can quickly calculate the M. M is N1 N2 by N1 square into L1. So L1 it's already given 3.6 Henry, and N1 into N2 is 3 to the 6 and divided by N1 is 9 multiplied by 3.6. So how much is this? 3 twos, 3 threes, 3 1.26, 2.4 Henry. Every time they ask you something, you get these relations in terms of the quantities which you know. Go with the basic formulas, and it won't be that much difficult. Okay, now we are flowing a 2 amps DC current through the two series connected coils. Then how much electromagnetic energy will be stored in the two coupled coils? So if there are two coupled coils, usually the electromagnetic energy stored in a single coil would be half Li square. So that we have derived. Now we also derived what would be the energy if there are two coupled coils. So one will be half Li square, that is self-stored, and one will be half L2I2 square, that is self-stored, and there will be some mutual component Mi1 I2. I doubt you remember it. Half L1 I1 square plus half L2 I2 square minus Mi1 I2. Now the direction of that plus M1I2 minus M1I2 will depend on the dot polarity. So we already know A entering and C entering. If we assume that way, so it will minus Mi1I2. So because the coil would be in this fashion, right? This here and here. Yeah. So by drawing the equivalent circuit, you can easily remember this formula, because in the derivation which we discussed in the week, in the theory concepts, we discussed for the plus Mi1 I2 case. So where the dot will be at the opposite ends, it will give a voltage source of minus plus M1 I2 here. So that will become in the formula, but here it is minus Mi1 I2. So if you want to quickly derive it, we can derive it, but it's your wish. So see, it's nothing. It's just a two voltage sources would be there. So I'm just drawing it. Here it is the voltage source. The primary side I'm drawing. So there will be two voltage sources here, and there is another two voltage sources here in series with 3. Now these two are connected in series. So this is E1, right? And this is E2, both sides. And this will be the self voltage source, plus and minus j omega L1 I1. So here it will be the polarity. I will request you to refer to the theory class. So the polarity is important here, minus and plus. Here it is minus and plus, the mutual one. So j omega Mi2, it is j omega Mi1. So the currents are important. I2, because it's mutual, depends on the current flowing through this. Here it is I1, depends on the current flowing through the first coil. Again it is same, plus and minus j omega L2 I2. So here you will have two equations. E1 is equals to L1 di1 by dt minus M di2 by dt, and E2 also you will have two equations, L2 di2 by dt minus M di1 by dt. So You have to calculate the energy, right? Energy, in order to get the energy, you need to get calculate first the power. So power would be E1 I1 plus E2 I2. After getting P, you have to just to differentiate it with respect to time to get the dW. dW is equals to P into dt. So this power expression multiplied by dt. So you will get L2 I2 D1, L2 I2 D2, like that term, and then you just have to W would be half Li square plus half L2 I2 square minus M I1 I2. So that's how you get, since the series current I1 and I2 are same as 2, you know L1, you know L2, you know M, I1, I2 would be same. So you just substitute and get the answer. So I would request you to refer the recording of the second week, or no, first week's discussion where we have derived this expression. So yeah, okay. Now you remember the second weeks of discussion where we were discussing the Fleming's right hand rule and left hand rule. So using those rules, we will decide the polarity and magnitude of the voltage, and left hand rule we will use to determine the polarity and magnitude of the force, right? So left hand rule is like a motoring operation. You get some motoring motion, and in the right hand rule it's a generating operation because it generates electric voltage between any 2 points in the right hand rule. So okay, so this is the thought experiment, some imaginative setup we have here. The length of the cord L is zero point 0.4, flux density is given, resistance is given, all others are negligible, frictional forces are negligible, so everything is ideal. So the conductor is pushed with a constant force of 100 millinewton. Okay, we know the force here. So at steady state, the conductor will move at a constant speed and a constant EMF will be induced in it, which will drive a constant current through the resistance. That's true. Whenever you are giving an external force placed under a magnetic field, so the conductor will move at a speed and EMF will be induced, right? And what is the question here? The question is estimate the current that will flow through the resistance in the steady state. So we are requested the current here. So we were given the values of B, length of the uh, zero point 0.4 is the length of the conductor, and we also know the force. So can someone tell me the formula you can remember? At steady state, the electromagnetic force equation would be,
ELB, sir.
sorry,
F equal to ELB.
yeah, BIL. Now B we know, I we know, and I we need to calculate F. So the current would be F divided by B multiplied by L. So F was given how much? It is 100 millinewtons. Density, how much it is given? Zero point 0.8 Tesla, right? Yeah, flux density is zero point 0.8 Tesla, and length of the conductor is zero point 0.4. Make sure the units, okay, it's in newtons, it's in Tesla, and it's in the meter, or are in SI units. So you need to make sure all the newtons, because silly mistakes can happen even if you know the formula, everything is correct, substitution is correct, the concept is correct, but if your units you miss it, it would be a very silly mistake you could do. Now, yeah, current you can calculate it. It would be around 312.5 milliamps. So the quickest would be to answer this question fast. As quick you strike the formula of force, formula will be BIL. In the similar way, the induced EMF, the right hand rule, will give you the formula E is equals to BLV, where B would be the flux density, L is the length, and V is the velocity. V is the voltage. So E is equals to BLV. So there also you can get the this equation. Now see, induced EMF, maybe the next question should be that only. Yeah, induced EMF. Now to calculate the induced EMF, we need to just get the voltage, and we know I and R. I we just calculated, resistance is already given in the question, 1 ohm resistance. So induced EMF would be 312.5 milliamps multiplied by 1. So that would give you the induced EMF. Now steady state velocity. So whenever you are placing a conductor in a magnetic field and it experiences some force and it moves with a velocity. Now this again comes to the right hand rule where we can get the formula of E is equals to BLV. Now here V is velocity, but it was asked to be centimeters per second. That's again an important thing which you have to keep in mind. Now E induced EMF, we just calculated it. Uh, how much it is? 312.5 into 10 power minus 8. So 312.5 millivolts. The required thing is velocity, E by BL. So E is 312. It's in still SI unit, and B is in zero point 0.8 into zero point 0.4. Now, if you calculate it, you will get a 0.9766 meters per second. So the required question is in centimeters. You just have to multiply with 100, 97.66 centimeters per second. So the idea of solving these questions is not just concept is important, but also what has asked in the question, what you are supposed to write. Is it in meters per second or centimeters per second? The question requirement is also very important. Okay, now we have to estimate the power in milliwatts required to keep pushing the conductor to the steady state. So now you know the. I would ask you what would the formula for power? You know the velocity, you know the force. I already gave you the hint now.
Yes, sir.
Power is equals to force into velocity. Right. Now force it was already given when pushing the conductor with the 100 millinewton. And velocity we just calculated it in the meters per second. You need to calculate 0.9766 meters per second. Both are in SI units. Now, if you calculate, it will be 97.66. This is 100 here. 97.66 milliwatts. Right? There is another formula. P is equals to I square R. You can calculate that also. It should also give the same result. Okay. Okay. Now let's proceed to the another concept where we will be discussing about the winding schemes and winding terminology. These are when we discuss it, it's very easy. But when you again look back into those, you might not recall everything. So for that purpose, I have picked one such problem which we have solved during the third week discussion. So here we were given the details of a generator, a 6-pole 3-phase 50 Hz generator having a length and diameter, slots, phase spread. It's a double layer winding. Assuming air gap flux density to be sinusoidal with B max 0.8 Tesla, coils have 4 turns each and are short coiled by one slot. So all the details are here: short pitch, double layer, slots, phase spread, everything is there. So I hope this will um, jog your memory in reiterating all the concepts. So first question was slot pitch beta. Beta in electrical degree it was asked. So now see, beta is nothing but the slot pitch. So if you know your machine is spreading 360 degrees electrically, so 360 degrees, sorry, 360 degrees mechanically, within that 360 degrees mechanical, you have placed all the slots. So each slot will take a bit of angle. Now how many slots do you have? 54 slots. Now this 360 mechanical, you have 54 slots. So on, so on, so on, 54 slots. So each slot will have some angle. So that is nothing but the slot pitch, which is beta. So first, let's calculate the beta and the mechanical. Mechanical would be very easy. It's visually easy to imagine anything in mechanical. Now, total 360 degrees divided by 54 slots. This would give each slot would carry how much slot pitch angle in mechanical. So 360 by 54 would give you 6.66 mechanical degrees. Now it was asked to find it in the electrical degrees. So how many poles is this? 6 pole. So what's the formula to convert the mechanical degree into electrical degree? Beta electrical is equals to beta mechanical into pole pair. 6.66 into 6 by 2. 3 and 6.66 into 3, it will give you 20 degrees. So that's the slot pitch in the electrical. So there is another way also. So you know slots per pole. Now the poles are 6 pole, and slots per pole will directly give you how many slots are under each pole. So it's a 6 pole machine. There are 54 slots. So each pole would have 9 such slots as per S by P. 54 slots divided by 6 pole. So 9 slots per pole. Now each pole have a 180-degree electrical. That also we know. Now each per pole we have 9 slots, and each pole would spread over 180-degree electrical. Now how many slots per pole? We have 9 slots per pole. So per pole is having 9 slots. So this is 180-degree spread. So we know 180 and there are 9 slots. So it will be easy. So already electrical 180 by 9 would also give you 20-degree slot pitch. So that's another way. You can go through the mechanical way or the electrical way. Anything is fine. But remembering the concept is important. Okay, now second question is a rated speed in RPM. RPM would be 120 F by P. It's in radians per second to do omega. Now N is equals to 120 F by P. Simple. I'm not solving it at 120 into 50 Hertz by P 6 pole. You can solve it. Flux per pole in milliweber. So yeah, this is a important formula. How to calculate the flux per pole? The flux per pole, if you know the flux density Weber per meter square and you multiply it with the area, you would get the flux Webers. Now the B max, which was already given to us, and you need to get the area. And any idea you can do that? This is a derivation which we have done in the form question in the theory. We can do that, but there is another simple uh, formula for it. Okay, so flux per pole the is equals to, so B max, ultimately it's B into area only. So we were given this maximum sinusoidal density. So B max by pi by 2 would give you the average one multiplied by the area pi dl. This is per pole. So now pi would get cancelled. There is a pole here, and 2 by pole multiplied by B max multiplied by dl. So this is the formula to calculate it. So here 2 by poles and B peak that is already given, and length it is given, and R you can split the diameter into 2 times the radius. Radius was given in the question. You just substitute, you would get the answer. So this formula is important. B into area. B is maximum which is given. Average will be divided by 2. If you want to clear derivation, you can refer the class here. So it was minus pi by poles to positive pi by poles. The sinusoidal is B cos theta. So that derivation would give you the same. Anyway, the next question, yeah, pitch factor and distribution factor is also some important terms which will be definitely asked for the gate examination if there is a chance. It's the direct substitution. You shouldn't get confused here. Kp, I'm just writing the formula here. Kp is equals to cos epsilon by 2, right? This is the formula for pitch factor. But in the question, it was given that it's a short pitch winding. It was short pitched by one slot. It was given. So one slot pitch, it was short pitched. So each slot pitch is 20 degree. We have calculated the beta. Now the epsilon would be 1 times the beta. Someone already asked a doubt about this after the week in the recording video. So I'm saying that. So epsilon would be 1 times beta. 1 comes from the number of slots it is being short pitched. So here it is given 1 slot short pitched. So it is 1 beta. So if it is short pitched by 2 slots, it would be 2 beta epsilon. So epsilon is 1 into 20. Epsilon is 20 degree. So Kp, it's simple, cos epsilon by 2. You would get cos 20 by 2. Cos 10 degrees is the pitch factor. Now, if there is any other question, like what is the pitch factor for the third harmonic to eliminate it, then it should be 3 times, third harmonic means 3 epsilon by 2, right? Yeah, the same question. So here we are asked, if there were third harmonics, what would have been the pitch factor for third harmonic? So Kp is equals to cos 3 epsilon by 2. So don't get confused. If they're asking it is being short pitched by three slots and also to calculate the third harmonic, you have twice the three here. So short pitched by three slots means 3 into beta. Again, third harmonics means 3 epsilon. So it would be 9 beta. So you shouldn't have any confusion. So first calculate epsilon and then introduce the harmonic factor. Right? It will be cos 3 into epsilon is how much? 20, right? No, it's cos 60 by 2. It's cos 30.86. Okay. Yeah, and would be slots per pole per phase. You know all the three parameters. Slots 54 slots per 6 pole per three phase. It would be give you three answer. Yeah. Now comes the distribution factor. It the formula it would be in terms of sine. It not in the cos terms. Sine m beta by 2 divided by m sine beta by 2. So they here the m would be the you can take it as a phase spread the slots per pole per phase. It's not the harmonics m. Okay, m would always be there even if it's a fundamental or any harmonic. If it is harmonic, you will have to make it the beta as three times. So here we have calculated m is equals to 3 slots per pole per phase. Sine 3 beta by 2 divided by 3 sine beta by 2. Beta we already calculated 20. You can substitute. Now the next question if you see, it was asking the distribution factor for the third harmonic. Right? If you are going for the third harmonic, now the formula would change as sine m 3 beta by 2 divided by m sine 3 beta by 2. So this is what I'm saying. You have to be careful. So first calculate the pitch angle, how much it is, 3 beta, and then m would always be there. Take care of it. Okay, number of coils. So this is another key data which we shouldn't miss in the question. It was given that it's a double layer winding. So I'm just showing you briefly. If it's a double layer winding, there will be two slots, upper slot and lower slot. Now, if it is going like this, it will come back and sorry, come back and it will go from the bottom. Now, if it is going from the bottom, maybe it will come and come back like this. So now, if you see, these two slots are having two coils, right? Because of this lower and upper deck arrangement, two slots will arrange for two coils. So in the double layer winding, the formula is number of slots is equals to number of coils. So it is 54 slots. So the coils will also be 54. Okay, got it. Okay. Now, what is the RMS value of the EMF generated per coil group? Okay. Now, EMF, we know we already know the formula. So the coil group is what you need to be sure of. So coil groups are there are 54 coils because of the slots, and how many such coils are per pole?
So,
Yeah,
but this makes it much more expensive. This really group selection.
I can't understand you, Ganesh. Can you type it in the chat box? There is a lot of disturbance from your side.
Now,
I can hear you, but it's very muffled voice and very muffled. You can type it in the chat box. So the question it was given, coils have 4 turns for each coil. Given coils have 3 turns. Can you move close? So I'm getting an echo. You can type it if you want to say something. is equals to root 2 pi kp kd phi.
Yes, right? You are reading, right?
I'm sorry, your voice is very muffled. You can type it. You can type it. Or is there any fan interrupting your voice? You can switch off the fan and try to type.
Hello?
Yeah, yeah, Dinesh.
No.
Yeah, you can speak now. I think it's clear now.
You are reading, right? No, so this coil group, at that time also, I could not understand.
Okay, coil
So
group.
if you can explain us for two pole, 4, 6 pole, coil group and be a series and parallel connection
Okay.
for getting maximum current and maximum voltage.
Okay, coil group I'll explain now. So the coil group has to do with the term T here. So the turns per coil group. So first calculate how many coil groups are there and then multiply it with number of turns. So in the question it was given for 4 turns per coil. Okay. Now this turn should be how many turns per coil group. So once calculate the coil group and multiply with the 4. Simple, no confusion. Now to calculate the coil groups. So there are 54 coils. When they say a group, they mean that how many coils are there per pole per phase. So if you can calculate that number, how many coils are there per pole per phase? So there are 54 coils. How many poles? It's 6 pole machine. If it's a 4 pole, a 2 pole, you divide it like that. And per phase. So it's 6 9s and 3 3s. So it says that for each coil group, there are 3 coils. Okay, understood? Now in the question it was given that each coil is having 4 turns. So this T is the effective turns. Since we are calculating this EMF per coil group, each coil group will have 3 coils and the turns here would be 3 multiplied by 4. So each coil would have 4 turns. So the T is equals to 12 here. Now you just have to substitute root root 2 times pi kp kd phi f and t. The t is the key here, but the coil group means per pole per phase how many coils are there. So once you got the number of coils per pole per phase, multiply with the number of turns per each coil you have. That would give you the coil group turns, and it's just a substitution there. Okay, this is a winding scheme only. I don't know if I should repeat this or not, but it's just important thing. If you understand the logic, you can solve it in 5 minutes. It won't even take 5 minutes. So you just observe what is the spread here, 10, and then you quickly calculate the beta from here, and then start do solving it. You find how many total slots are there. See here you can see there is a 48 48 slots are there, and coils per pole, number of coils, it's a clearly a double layer winding. So one and dash it's there is double layer winding. So there are 48 coils in the double layer winding, 48 slots. So slots, there is a 4 pole. See this is a 1 pole, second pole, third pole, fourth pole. 4 poles are there. So slots per pole we can calculate 48 by 4, 12. So you can get the beta now, 180 by 12. So you get the beta 15 degree. So just after seeing the winding diagram, just quickly calculate all the terms, beta, slots per pole, coils, everything. So now you can just calculate the next numbers. That's okay. Once you get the beta, you can easily calculate the pitch, how much the coil span is. Okay. See, 1 to 11. Means the span it is 10 slots, right? So each slot is 15 degree. So 10 slots would be how much? 150 degree. So the coil span is 150. So since the coil span is 150, beta is 15, coil span is 150, and you can say it is short pitched. Usually coil span is 180. You got 150. That means it is short pitched by 30 degree, right? That is epsilon is 30. So once you calculate all these epsilon and all, you can directly calculate whatever the question was asked. The coil span we just calculated. Coil span is 150 degree. Beta, you know that between each slot is 15. Coil span is 150. And next one it should be pitch factor Kp for third harmonic. Kp is cos 3 epsilon by 2. We just saw epsilon is 30. It is short pitched by 30 degree. And cos 3 epsilon by 2 for third harmonic. And phase spread. How See, first you need to calculate how much is the slot pitch for phase spread. So slot pitch it's 15 degree. Now each phase is spread across how many degrees you need to calculate. So for that you calculate the slots per pole per phase M. This will directly give you the phase spread. So S per P by phase. So number of slots it is 48. 4 pole machine, 3 phase. So how much it is 4. Now M is 4 and each slot pitch is 15. So each slot pitch multiplied by 4. 4 slots per pole per phase will be each phase is spread across. So it is 60 degree phase spread. So that's it. And distribution factor.
Hello?
Yes.
M beta is the phase spread.
Yes.
Can we say like that?
Yeah. M beta is phase spread. Correct. Now distribution factor for third harmonic KD sine M k beta by 2 by m sine k beta by 2, where k is the harmonic, I would say. M is here this slots per pole per phase, and k is third harmonic, beta is 15 degree. So it's simple. Yeah, XYZ, you can complete it with the coil span and all. You can just quickly solve all the XYZ values. It should not be difficult. Okay, now just we have only 10 minutes left. Let's just quickly look
Sir,
into. Yeah,
sir, now we calculate the coil group now,
uh,
that 4 into 3.
right.
Okay, and we calculated a voltage for per coil group.
Yes.
Now there are how many coil groups are there in that question?
The coil groups are number of coils per pole per phase. We got 3 coil groups.
Three coil groups.
Yeah.
So suppose I have to connect series and parallel of each coil group to enhance the rating of voltage and current.
Okay.
There was a question like that in the assignment.
Yeah, yeah.
Suppose I know it is a three coil. Yes,
Tell me
actually that is not clear. Still, that is not clear to me.
that question. Do you have? You mean to say when
Yeah,
three
I'm
coil
having.
groups are connected in series?
No, the question is like that. I
Uh,
have calculated voltage for the coil group
okay.
that you calculated.
Huh.
Now, how many coil groups are there? We have to connect them in series and parallel to get a maximum voltage rating and maximum current rating.
Okay. Yeah, yeah, yeah. Huh. Okay. That's the
Then,
question.
what will the maximum kVA rating?
Okay. Let
Yes,
me.
that question.
Okay. I just have to check that question once. Let me just go through. Is it the If all the coil groups are connected in series, then the RMS value of the voltage, is that the question? No.
Yes, sir.
Okay, okay. So now if all the coil groups are connected in series, then we are asking the RMS value of the total EMF generated. So for the RMS value of the EMF per coil group, we got some 100 volts or something. Now you need to calculate number of coil groups are all are connected in series. So number of poles, 60 degrees. Okay. Now we need to calculate number of coil groups for each pole. All are connected in series. So for each coil group, it is no. What we calculated is the coil group. Okay. For each coil group, no. Three coils. It's okay. Okay. Sorry. So here the three is number of coils in each coil group. So three is not the total coil groups, but each coil group will have three coils. That's okay. Now we need to calculate how many coil groups are there in total. Now that we can get from, I think, space spread. Uh, Here the coil groups is 1, 2, 3, 4, I guess. So if I need to calculate in such a way, how can I get that? I need to calculate the phase spread here. How much is the phase spread? And beta is the phase spread here. So
So
here
it is given, sir, 60 degree.
phase spread is given.
Yeah,
Okay, okay, 60
in
phase spread is
the
given.
start of the question.
Okay. Now 60 phase spread and 6 poles. How many coil groups will be there for 60 phase spread? Slots per pole per phase. Okay, number of coil groups would be each, if it is one, this is under one pole, this is under another pole. For each pole would have one coil group. Right? It's a 4-pole machine. Okay. Coil group or phase would be 4. In that logic, here, how many phases are there? Sorry, poles are there? 6-pole machine. Okay, yeah. You got the solution for this also, right? I think EMF per coil group would be 107, and you just have to multiply it by 6 number of poles. Because see, in this is one example. This will make our understanding very easy. For each pole here, we are having a single coil group. So this coil group. Now, based on this number of poles you will have those many coil groups. So here we have 6 poles, and 6 poles will have 6 coil groups, and each coil group will have 3 coils. That's okay. But here, for directly the answer would be, if per coil group it is 107.5 volts. Now for the total EMF would be, for multiplied by 6 coil groups, it would be 107.5 into 6. That should be the answer. You understood, Dinesh?
Coil groups is equal to 6 poles.
Yeah, 6 poles. Each pole would have one coil group, and within that coil group, within each coil group there are 4 winding, 4 coils. So, but in our case, we will have six poles, and each will have three, like that. One, two, three, four, five.
What about the phase spread here, sir?
I don't think phase spread matters here because since the phase spread is 60 degree and there are three phases 60, 60, 60, 180. So if it is not a NPTEL is not 60 degree, then it might create some difference. Since it's 60 degree phase spread, each phase is spread across 60 and three phases would evenly spread across 180 degree. So for 60 degree phase spread, number of poles should be equal to your number of coil groups. That's what I'm thinking. So what happens if the phase spread is not 60? I'm not yet sure. I should have to look into it. But yeah, but since the given problem has
So there are six coils.
right,
I can connect them in series,
right,
okay?
right,
And one coil group having four coils,
three coils,
three coils.
right,
And turns is four. So go to four into three is the coil group voltage. Then multiplied by six will be they are connected in series. They will give me the maximum voltage rating.
right.
What about the maximum current rating?
In series, it's only series same current would flow. If you want to connect in maximum current rating, you need to connect in parallel. The voltage will remain same.
How so? Like current will increase six times.
If you are connecting
If
six
six
coil
coil group
groups,
beside
if you are connecting six coil groups
in
parallel,
parallel.
it would increase six times. Yes.
That is correct, no, sir?
Yeah. Right. Connecting parallel, it would increase six times. There are six coil groups you have. Ultimately, if you want to increase current connected in parallel, six times the current would increase. If you want to connect in series, voltage would increase six times. That's correct.
Okay.
Okay, fine. I think we are out of time now. It's okay. Induction machine. It's a simple concepts only. It's only the speed of fields with respect to stationary observer and that here and there. Questions will be what is the speed of rotor field with respect to ground, and such questions will be there. And yeah, rotor current starting, rotor power factor at the starting, torque at the starting. So these formulas I hope you remember. See, ultimately you need to remember the equivalent circuit of the induction machine. Everything would be solved. So from that you calculate the rotor current. I2 is equals to like SE2 would be there, root of R2 square plus SX2 square. So this will give you rotor current. So at the starting, substitute S is equals to 1 and then you will get the starting rotor current. Now rotor power factor at the starting. So power factor is nothing but cos 5 is the power factor. It's R divided by Z. So R resistance, Z is the equivalent impedance, you get the power factor. So they will ask the torque at the starting. See the torque at starting, torque is nothing but air gap power by 2 pi ns. Now air gap power, you need to calculate all the losses for that. So whatever is the 3 I square R losses you need to calculate. 2 pi ns you know, torque you will get eventually. Now they are asking for a different speeds means nr you will give, slip you calculate ns minus nr by ns, same formula, same rotor current formula, s will change and then rotor power factor r2 by r2 square plus sx2, s would change, same thing, torque will also change. So yeah, that's it. Okay, everything would be similar fashion only. That's it. I would suggest everyone to go through the recordings again and focus on the numerical parts. Of course, theory is also important. That's how we arrive at the numericals. But it would give you a good summary of all the questions we have discussed. So yeah, we will meet this Tuesday, our usual time, 6 to 8, and that would be our last week discussion. We will discuss some good concepts on the synchronous machines, and we will be closing our session for this semester. And yeah, let's meet Tuesday. And thank you for coming to this extra session and patiently listening to this numerical discussion. Thanks for actively participating, you three. And yeah, thank you for attending, and I will see you for one last week in the Tuesday. Thank you.